almost everything you see, the buildings, the bridges, the very ground beneath our cities, it's all built from concrete. It is the literal bedrock of modern civilization. But what most people don't realize is that this silent, strong material holds a secret, a fundamental flaw that could change everything we think we know about building for the future. So here's a wild thought. What if the very stuff we build our world with wasn't just dead stone? What if it were something more alive? Imagine cities that could mend their own wounds, just like a living thing. The answer, believe it or not, lies in a flaw that we see every single day, but we never really see. Okay, so to really get this revolution, we first have to talk about concrete's one universal flaw. The one big problem with the greatest building material humanity has ever come up with. And yeah, it's been hiding in plain sight this whole time. And here it is. It's shockingly simple. Concrete always cracks. That's its secret weakness. Doesn't matter if it's from stress or heat or just time. Tiny little fissures start to form, and you might think, so what? Well, these small cracks, they're like open invitations for water and chemicals to just seep in and start eating away at the steel reinforcement from the inside out. It's a slow decay that leads to incredibly costly and constant repairs. And look, the cost isn't just about money. Think about the cycle. We produce it, we pour it cracks, we replace it. That whole process is massively energy intensive. So much so that concrete production alone is responsible for nearly 10% of all global CO2 emissions. Let that sink in. 10%. We've basically designed the most used material on Earth to decay. And that decay has a huge environmental price tag. But what if we could break that cycle? What if, instead of constantly fighting against nature, we just invited it in? This right here is where the story pivots. This is where science fiction starts to become science fact. Let me introduce you to bioconcrete. And yeah, it's pretty much exactly what it sounds like. The idea is to embed specific, totally harmless bacteria right into the concrete mix itself. What you're doing is creating a material with a built-in immune system. You've got these little microorganisms just lying dormant, basically sleeping, waiting for the one thing that signals damage has occurred, a crack. So let's just break this down, because this is the key. With the concrete we use now, a crack is the beginning of the end. It's a weakness, it's decay. But with bioconcrete, a crack is the trigger. It's the starting gun for regeneration. The problem literally becomes its own solution. That is a total game changer.
All right, so the big question, right? How on earth do microscopic bacteria fix a crack in solid rock? It sounds impossible, but the process is actually surprisingly elegant. It's a natural phenomenon. Don't worry about the long, sciencey name. All you need to know is it's a pretty simple 5-step process.
Okay, here's how it goes. First, a tiny crack forms. Now water starts to seep in. And here's the cool part. The very thing that would normally destroy concrete, the water, instead acts as an alarm clock. It wakes up those dormant bacterial spores. As soon as they're awake, they get hungry, and they start to feed on a nutrient source, like calcium lactate, that was mixed right into the concrete with them. And as they eat, their waste product is, get this, calcium carbonate, basically limestone. And that limestone crystallizes, it hardens, and it seals the crack completely from the inside out. Yeah, you can really think of them as microscopic construction workers just on standby, ready to patch things up the moment there's a problem. It's the perfect biological partnership, The bacteria get a safe home, protected inside the concrete, and in return, they make sure that home survives. A living repair crew, on call 24/7 for decades. And when you look under a microscope, the proof is right there. What you're seeing are those dense calcite crystals, that's the CaCO3 that the bacteria produce. They form this incredible, permanent seal. It's not just plugging a hole, you see. They are literally rebuilding the structure, making it solid and impermeable all over again. But here's where it gets even crazier. This healing process, it does way more than just patch cracks. The latest research is showing that just by being there, these bacteria make the concrete fundamentally stronger, right from day one. So first up, let's look at compressive strength. That's basically the concrete's ability to resist being crushed. The massive weight of a skyscraper just pushing down on it. And the data is clear. After just 28 days, the bioconcrete with a high concentration of bacteria is already significantly stronger than the regular stuff. Okay, next we test its split tensile strength. This is all about its resistance to being pulled apart. Think of the forces that try to stretch a bridge. And wow, the improvement here is even more dramatic. We're talking about a massive leap in performance, a huge boost in durability. And finally, we've got flexural strength. It's just a fancy way of saying how well it resists bending before it snaps, like a concrete beam holding up a floor. And again, a clear, powerful improvement. So look, the main takeaway here is crucial. This isn't just about self-repair anymore. It's about creating a superior, higher performance material right from the get-go. So how is it doing all this? Well, the bacteria don't just wait around for big cracks. Their constant activity fills in the microscopic pores inside the concrete itself. Think of regular concrete as being slightly like a sponge. The bacteria basically clog up all those tiny holes, making the whole thing denser and way less porous. This creates a powerful shield against all the stuff that causes long-term decay, like water and harmful chemicals. When you step back, you realize this technology could change more than just our materials. It could change our entire philosophy of building. It's pushing us past just sustaining what we have and toward a world that actively restores itself. For the longest time, the whole goal of green building has been sustainability, right? Which really just means doing less harm, reducing our negative impact. But regenerative design asks a totally different question. It asks, how can our buildings actually do good? How can they become active, positive parts of the ecosystem? Bioconcrete is a perfect example of this. It's not just about reducing waste. It's about creating a structure that actively maintains and restores itself. So, what's the bottom line? Why does any of this matter to you and me? Well, it means our bridges, roads, and tunnels could last for decades longer. It means we'd save incredible amounts of money on maintenance and waste fewer resources. It means a much lower carbon footprint for our cities. And ultimately, it just means safer, more resilient infrastructure that can actually stand the test of time. What we've done here is embed a biological process into an industrial one. And in doing so, we've created something totally new. A material that isn't just built, you could almost say it's born. It kind of forces us to erase that hard line we've always drawn between the artificial and the natural. So the final question isn't just, can we build a world that lives? It's, what's it going to mean for all of us when our cities finally wake up?
Don't go anywhere, hit subscribe, and we continue.
You've seen it 1,000 times, right? That little helicopter seed spinning its way down from a maple tree. It just looks like this simple, lazy dance with gravity. But what if I told you that simple little fall is actually a masterclass in aerodynamic engineering perfected over millions of years? And here's what most people don't realize. Hidden inside that hypnotic swirl is the blueprint for solving one of our biggest urban energy problems.
So what is going on here? Well, it all starts with understanding the seed's mission. The official name for it is a Samara, and it really only has one job: to fly. But it's a very special kind of flight. It's not about going fast or generating power, it's all about staying in the air, defying gravity for as long as it possibly can.
You see, this spinning, this auto-rotation, it's not just for show. It's a brilliant survival strategy. By slowing its descent, the seed is literally buying itself time. And more time in the air means a much better chance of catching a gust of wind and traveling far, far away from the shadow of its parent tree. It's a simple goal, sure, but it's achieved with an incredibly sophisticated piece of natural engineering. And this is where the ancient world smashes right into our modern one. What on earth could this tiny biological blueprint possibly teach us about powering our massive concrete cities? Well, the answer, as it turns out, is pretty much everything.
To really get it, we have to look closer at the physics of that spin. This is no random tumble through the air. Nope. It's a highly controlled flight, and it's all built around one incredibly powerful aerodynamic principle.
It's called the leading edge vortex, or LEV for short. Now I want you to picture a tiny, perfectly stable tornado that the seed creates and just holds, right, on the leading edge of its wing as it spins. This isn't some chaotic random force. It's a consistent, powerful pocket of air, and it is the secret to this whole operation.
So how does this tiny tornado work? Well, the LEV creates a zone of intense low pressure right above the wing, and this pressure difference acts like a vacuum, literally sucking the wing upward, fighting against the pull of gravity. And this is not a small effect. It can actually double the lift the wing would normally be able to produce.
Now, this is what makes the Samara's design so revolutionary. A conventional aircraft wing has a critical weakness. If you tilt it too steeply into the wind, what's called a high angle of attack, the airflow just breaks apart, and the wing stalls, losing all its lift. But the Samara wing? It's completely different. It thrives at these extreme angles, using that stable LAV to generate continuous, powerful lift precisely where a man-made wing would just fail and fall out of the sky.
Okay, now hold on to that idea of stall-proof flight, because that concept is the key to solving a completely different problem. How do we generate clean energy right in the middle of our cities? You know, small wind turbines seem like a no-brainer for urban centers, but they run into this massive fundamental challenge.
See, unlike the smooth, steady wind you'd find on an open plain, urban wind is just a chaotic mess. It bounces and ricochets off buildings, creating all this unpredictable turbulence and vortices. This chaotic airflow makes conventional turbines wildly inefficient and super noisy. And that's not even getting into the concerns about safety, vibration, and just how they look in a crowded city.
To put it simply, the technology we've been using is just fundamentally mismatched with the environment we want to put it in. We've been trying to fit a square peg into a round, turbulent hole, and it just doesn't work. So we have a design from nature that actually thrives in chaotic airflow, and we have a city full of, well, chaotic airflow. And this is where things get interesting. This is where our little spinning seed re-enters the story. Faced with this urban wind problem, some engineers realized they didn't need a brand new invention. They needed a pre-existing, time-tested solution, and they found it hanging from the branches of a maple tree.
The result is a totally radical new approach. By mimicking the single-blade, auto-rotating design of the Samara, engineers have created a turbine that doesn't try to fight against urban turbulence. It's a design that's built to harness it.
And remember that stable leading-edge vortex? The seed's secret weapon to avoid stalling? That is the exact same mechanism that allows these new blades to handle the city's messy, unpredictable wind. So instead of stalling when a sudden gust hits it from the side, it just captures that energy and keeps on spinning.
And here is where the numbers get truly mind-blowing. The absolute theoretical maximum efficiency for any wind turbine, it's a physical limit known as the Betz limit, is 0.593. So what's the power coefficient of a falling maple seed? It's 0.59. Nature, through millions of years of evolution, has engineered a design that is quite literally knocking on the door of aerodynamic perfection.
And this isn't just some cool theory. Modern engineering tools, we're talking computational fluid dynamics and finite element analysis, are all confirming it. The simulations are showing that the single-blade, bio-inspired design is not only structurally sound, but it's aerodynamically superior in the exact conditions where traditional turbines just completely fail.
So, you see, this isn't just about building a clever new turbine. It's about a much bigger idea. It's about a profound and powerful connection between the natural world and our own technological future.
There's a name for this field. It's called biomimicry, and it's built on a really simple but powerful idea. Why on earth would we invent from scratch when nature has already spent billions of years doing all the research and development for us? The answers to so many of our biggest challenges are all around us.
The Samara Solution teaches us something really important. It shows us that innovation doesn't always have to be about brute force or creating something entirely new. Sometimes, the most elegant and the most effective solutions come from simply observing, understanding, and humbly learning from the designs that have already stood the test of time.
So the next time you see one of those seeds twirling to the ground, you won't just see a piece of a tree. You'll see a blueprint for the future. And it really leaves you with a powerful question. What other brilliant solutions are hiding all around us, just waiting in plain sight?
Don't go anywhere, hit subscribe, and we continue.
You know, concrete is one of those things we see every day, but we never really think about it. It's the silent, steady foundation of our entire world. It's in our homes, our roads, our bridges, literally the bones of modern civilization. But this material we rely on so heavily has a hidden critical weakness, a flaw that is, by its very nature, completely inevitable.
And here's the surprising truth about that flaw. Every single concrete structure is actually designed with the expectation that it will crack. Now, these aren't just little cosmetic issues. No, they're more like open invitations. They're pathways for water, for oxygen, and all sorts of corrosive chemicals to creep deep inside, reaching the steel rebar and starting this slow, invisible process of decay from within. And the scale of this problem, it's absolutely staggering. Just get a load of this. 42% of bridges in the United States are at least 50 years old. We're talking about essential infrastructure, stuff we use every single day, facing constant stress. And every single one of those tiny cracks is like a countdown timer, shortening its lifespan and leading to incredibly expensive and disruptive repairs. So, all of this brings us to a really revolutionary question. What if, instead of constantly fighting against this cracking, the material itself had a built-in response? I mean, what if, like a living thing, concrete could actually heal its own wounds? Now, here's what most people don't realize. The breakthrough solution to this ancient engineering problem doesn't come from better chemistry or stronger steel. Nope, it comes from biology. The solution is quite literally alive. We're talking about something called bioconcrete. And the concept is just as elegant as it is powerful. You take dormant, living bacteria and you embed them right into the concrete mix. These little microorganisms just lie in wait, totally dormant, ready to spring into action and start repairs the second they're needed, all on their own. And this is where the idea gets so cool. Researchers like Henke Jonkers at Delft University of Technology didn't look in a chemistry lab for the answer. They looked to nature. They were inspired by the way our own bodies heal a broken bone. And they thought, hey, can we replicate that process in the world's most common building material? So who are these tiny biological construction workers? Well, they're specific, totally harmless bacteria, mostly from the Bacillus family. And these aren't just any old microbes. No, they're chosen for their incredible resilience. They can form these protective spores and survive for decades, maybe even centuries, inside the incredibly harsh, high alkaline environment of concrete. Just wait. So how does this healing actually happen? It's basically a simple 5-step biological chain reaction. First, a crack forms, and that crucial element, water, seeps in. The water is the wake-up call for the dormant bacteria. They wake up and start to feed on special nutrients, like calcium lactate, that were added to the mix just for them. And as they eat, they produce calcium carbonate, which is essentially limestone. That limestone fills the crack, sealing it watertight from the inside out. Simple as that. And the results? I mean, you can see them for yourself. On the left, you've got a typical microcrack. But look at the right. After just a few weeks of being exposed to water, that very same crack is visibly healed over, sealed tight by the limestone that our microscopic masons have created. This isn't just a theory. It's a visible, functioning repair system. It's incredible.
Okay, but there's a challenge, right? The process of mixing concrete is violent. It's high pressure, it's intense. It could easily destroy these bacteria before they even have a chance to get into the structure. So how do you get these delicate living organisms in there safely?
The answer is protection. Scientists came up with some really clever methods that act like tiny life rafts for the bacteria. They encapsulate the spores and their food source in things like porous clay pellets, or these squishy hydrogels, or even tiny microcapsules. These carriers shield them during the chaotic mixing process, but they're designed to break open or release their contents the moment a crack forms, delivering the healing agents exactly where and when they're needed.
But this is where things get really interesting. This isn't just about plugging a hole. The healing process actually restores the structural integrity. Check out this data. With a higher concentration of bacteria, the concrete can regain about 85% of its original compressive strength. It's not just a patch, it's a real structural fix.
And it gets even more incredible. Get this. In some tests, the healed concrete becomes stronger than it was before it cracked. This one study shows a 132% regain in what's called splitting tensile strength. The limestone that the bacteria produce integrates so perfectly that it actually reinforces the material, making it better than new. So when you put it all side by side, you can see this is a true paradigm shift. With traditional concrete, a crack is basically the beginning of the end. It signals decay. But with self-healing concrete, a crack is a trigger for regeneration. We're shifting from a system that needs constant, expensive human intervention to one that's autonomous, more durable, and has a much lower cost over its entire life.
And the knock-on benefits are just massive. I mean, we're talking about potentially cutting maintenance costs in half, dramatically extending the life of our bridges and tunnels, and lowering the carbon footprint by avoiding that endless cycle of repair and replacement. It's a win for our wallets and a win for the planet. And believe me, this isn't just some niche academic project. The construction industry is paying very close attention. The global market for self-healing concrete is projected to just explode, reaching over $300 billion by 2027. That number tells you all you need to know about the confidence that this technology is moving from the lab into the real world. Which leaves us with a final, fascinating thought. By embedding a biological process directly into our building materials, we're fundamentally changing our relationship with the structures we live in. So you have to wonder, are we on the verge of creating buildings and bridges that don't just stand there, but that actually live? Are we entering an age of living architecture that maintains and repairs itself? It's an amazing thing to think about.
Thanks for exploring the wonders of nature with us. If you enjoyed this journey, support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.